This video will cover two sample inference procedures. This first problem describes a company with two shifts, a day shift and a night shift. Both are making parts that need to meet some specifications, and the manager thinks that there's a difference in the proportions of the parts meeting these specifications for the two shifts. So we take two samples here. We have samples from a day shift and a night shift, finding the proportion that meet the specifications, and we're asked to create a 96% confidence interval. It's asking us to estimate a value, so even if we didn't have this phrase there, we'd know it's a confidence interval. When we look at this, again, we're estimating a value that's a confidence interval. We're going to rule out chi-squared in linear regression because we don't have a table or a regression output. There are two samples, and the samples are categorical because the underlying question is this part defective, yes or no? That makes this a two proportion Z interval. That's what we call it. On the test, it might be described as a confidence interval for the difference between two proportions. If we're asked to calculate the standard error for a confidence interval, we're going to start off by calculating our two sample statistics, the two p-hats. We're going to make in one big square root a fraction for each of those samples. So we have a fraction for the day shift, p-hat times q-hat over n, and then again for the night shift. Plug in all those values, and we get a standard error of 0.025 or 2.5%. To calculate the confidence interval, we're starting off by finding the difference between those two proportions, those two sample statistics. We'll calculate a z-score using inverse normal for a 96% confidence interval and plug in all our values there. And we get our interval from negative 0.016 to positive 0.096. If we're asked to write a conclusion, remember that with two sample inference problems, we're always talking about the difference in either the means or proportions. We are 96% confident that the true proportion of parts produced within specifications created by day shift workers is between 1.6% lower and 9.6% higher than the true proportion created by night workers. Again, this is about the difference in those parameters. When we write this out, we're going to keep the order that we used to create that interval. So when we created the interval, we did day minus night. So we're talking about the day shift workers in relation to the night shift workers. This first percentage is lower because that one is negative. The second one's higher because that one is positive. Based on the confidence interval, do you think that the difference in the proportions is statistically significant or significantly different? For a question like this, we're looking to see is 0 within this interval, okay? And it is, which means that these are not significantly different. This is not a statistically significant difference. And that's because since we're talking about the difference in parameters, if 0 is in this interval, it's possible that there's 0 difference, or in other words, there is no difference. They're the same value, and any difference that we see is just because of natural sampling variation. So again, if 0 is in there, they're not statistically significantly different. If it's not in there, that's when we can say there's a difference. Describe the sampling distribution. Again, this is about the difference in those parameters. The sampling distribution for the difference in the proportion of parts made by the day shift compared to the night shift will be approximately normal with a center around 4% and a standard deviation of 2.5%. This is that standard error that we had gotten before. This is the difference in those p-hats. One was 0.94 and the other was 0.90. So the difference that we get in those sample statistics is going to go in the center of our normal curve, and it's approximately normal because it meets that success-fail condition for both samples. If we were asked to write hypotheses for a significance test to determine if there is a difference in these proportions, the null hypothesis for a two-proportion z-test is always going to be that there's no difference. They'll always be equal to 0. And then the alternative comes from the text of the problem. So is there a difference means it can be either positive or negative. It could be a less than or a greater than if it talks about one proportion being greater than or less than the other. Now we're being asked to recalculate the standard error for a hypothesis test instead of the confidence interval that we did earlier. These will be different, and it's because when we do a hypothesis test, we're always assuming that the null hypothesis is true. And in this case, the null hypothesis is saying that these two proportions are actually the same. There's no difference in them. It's not until we see a low p-value that we would reject that and conclude that there is a difference in the proportion of parts made by each of these shifts that meet specifications. So if they're the same, any difference that we see is just due to natural sampling variation, and there's actually some proportion kind of where they meet in the middle, and we're going to pool our sample to figure out what that is, or what an estimate of that is at least. Okay, so we take both our samples, we put it into one big fraction, and we're going to use this on the top of both of these fractions inside our standard error. So P bar, Q bar goes on the top of both of them. 0.92 and 0.08 would be on the top of each of those fractions. On the AP exam, they're likely to write it like this, where they factor that P bar, Q bar out in front of the parentheses, and we just have 1 over each of those sample sizes. So if this were a multiple choice question, we'd be looking for something like this as the standard error for a hypothesis test. If it was a confidence interval, we keep the P hat and Q hat for each of those samples. So we would have the day shift P hat times day shift Q hat over the sample size for day shift, and then same thing just with the night shift data. When we calculate the test statistic, we're just going to look at the difference in those two sample statistics, compare that against the null hypothesis, saying that there should be a difference of 0, and divide by that standard error that we just found. Before we get into our next question stem, we're going to practice naming the method. Estimate the length of time that it takes the average letter sent locally to arrive at its destination. 92 letters were sent to various local addresses. So since we're being asked to estimate the length, this is a confidence interval. We don't have a table or a regression output, so we're going to rule out chi-squared and linear regression. There is one sample here, and it's a quantitative variable. It's how long it takes to get to its destination. This would be a one sample t interval, and it could also be called a one sample confidence interval for a mean. Is gender a factor in a person's favorite fruit? 400 men and 500 women were asked what their favorite fruit is to see if the distribution of favorite fruit is the same for men and women. Now, this one, if you were given this as an FRQ, it would give you some additional stuff, which I think would make it clearer to you which type of test it would be. But since we're just naming the method, it's a little more ambiguous. So to start, I'm going to highlight some key phrases here. So it's talking about a distribution of favorite fruit. It's not a proportion, it's not a mean, it's an entire distribution. It's asking, is it the same for men and women? So to start, it's a yes or no question. This is a hypothesis test. If we were to take a step back and think about how this data would be presented to us, we would have a sample for males, a sample for females. We would have those favorite fruits that they chose, and it would be arranged as a table. So if this were an FRQ, you would probably see a table like that in there, or it would write out this, which is a little more complicated to explain, but it can give it to you verbally. So that said, it's a chi-square test. Now we have to decide what type it is. We have two samples here, 400 men and 500 women. This wording is also cluing us into the fact that this is a chi-square test of homogeneity. When we have two samples, it's always going to be homogeneity because we want to see if those samples are the same or different. Do bears that raid trash cans have a higher rate of survival over a 1-year period than bears that do not raid trash cans? That's a yes or no question, so this is a hypothesis test. There's no table or linear regression output, so we'll rule out those two options. We're going to count up the samples, and we see that there's 34 bears that raided trash cans and 34 that did not. And then the underlying question, did they survive the year, yes or no? That's categorical. That makes this a two-proportion z-test, which could also be called a hypothesis test for the difference in two proportions. On to the next question stem. This one's about ACL surgery and how long it takes to recover. We have an old existing procedure and a new procedure that's been developed to reduce that recovery time. We'll see we have two samples here, existing procedure and new procedure. And the question is, does the new procedure result in a faster mean recovery time? That's a yes or no question. It's a hypothesis test. We'll rule out chi-squared and linear regression. Two quantitative samples because the underlying piece of data being recorded is how long does it take to recover from this surgery. That leads us to a two-sample t-test, which could also be called a hypothesis test for the difference of means. Show the equation for the standard error of the sampling distribution. To start, let me just define the variables here. Mu n will be the new procedure. mu e is going to be the existing procedure. Up here, I've summarized all that important information from the problem for each of those variables. And if we were to calculate the standard error, each of these variables is going to get an s squared over n inside the square root here. So we'll start with the existing procedure, 34 squared over the sample size, 34 squared over 110. And then we do the same thing for the new procedure here. Square root them, and we get our standard error. If we want to calculate that confidence interval, we'll start off by just subtracting those two sample statistics. That's our estimated difference, and then we're going to add and subtract our margin of error. Now for the t-score, we need degrees of freedom, and it's not as simple for two sample tests. This we're just going to get when we plug this into our calculator and run the test. It'll tell us the degrees of freedom is something. It'll be a weird decimal. Just write it down somewhere in the problem, and that 4.35 will go here. So we get a confidence interval from 23.76 to 38.24. Write a conclusion for the confidence interval. Again, this is about the difference in means this time instead of proportions. We are 90% confident that the true mean recovery time using the existing procedure is between 23.76 and 38.24 days longer than the true mean recovery time using the new procedure. Just like proportions, when we write this out, we're going to keep the same order that we used when we created the interval. So when we created the interval, we did existing minus new. So when we write this, we're relating the existing procedure to the new procedure. It's longer because both of these values up here are positive. In part E, we're asked to write the hypotheses. And again, we'll have a null hypothesis saying that there's no difference here. In this case, the alternative is that it's greater than 0 because if the new procedure is effective, the old procedure will take longer to recover and it will be quicker. Calculating the test statistic is just like proportions, except it's a t-score instead of a z-score. We'll start with a difference in those two x bars, our sample statistics. Compare it to our null hypothesis, which says there is no difference there. A lot of times we just leave these parts off and divide by the standard error. We get 7.12. If we wanted to increase the power of the test, there's two ways we can do it. We can increase the alpha level, or we could increase the sample size. Increasing the sample size is more time consuming and costly, but it has an added bonus of decreasing both the type 1 and type 2 error probabilities. If we increase the alpha level, all right, that's going to affect both type 1 and type 2 errors. Type 1 errors occur with alpha probability. So if our alpha level is 5%, we're going to get type 1 errors 5% of the time. That said, if we increase the alpha level, type 1 errors are going to increase also. Type 2 always moves in the reverse of type 1. So if type 1 goes up, type 2 goes down, unless, of course, we're talking about increasing the sample size, which reduces both of them. When we check the conditions for a problem like this, make sure you check them for both samples. So when we do randomization, we want to make sure we talk about both the samples being randomly assigned to these two treatment methods. Same thing with 10%. We're talking about both samples here being less than 10% of their respective populations, people who could receive these procedures. 110 and 100 are both greater than 30, so we can apply the central limit theorem, which is going to state that we end up with an approximately normal sampling distribution. And then anytime we do a two-sample test, there's a fourth condition called independent groups. And this is with respect to the response variable. So our response variable here is recovery times. And we're just going to say that recovery times for these two procedures will be independent because they're being randomly assigned. We'll close out with a few more name the method examples. How many fewer calories do vegetarians consume compared to meat eaters? We have 90 vegetarians and 90 meat eaters who are monitored for their caloric intake. We're being asked to estimate some difference. That's a confidence interval. We'll rule out chi-squared and linear regression. There are two samples here, and it's a quantitative metric. This is a two-sample t-interval, which could also be called a confidence interval for the difference in means. Over the past many years, the average daily attendance at the theater was 147. This year, 40 randomly selected days produced a mean of 150. Has attendance improved? That's a yes or no question. It's a hypothesis test. Again, we'll rule out chi-squared and linear regression. This time we just have one sample, and we have a quantitative variable again. So this is a one-sample t-test or a one sample hypothesis test for a mean? And don't X out yet because this is a tricky one. Do people spend more time working or sleeping? 200 people were asked how many hours they work and how many hours they sleep. Hypothesis test, cross out chi-squared and linear regression. All right, now next up, when we look at this, we see just one sample of people. However, there are two samples here, and that's because they're being asked two questions. How many hours they work and how many hours they sleep. So we have two samples here, but these are not independent samples. These are dependent samples, all right? When we collect data on the same people and ask them two different questions, a lot of times it's talking about something like a before and after, like maybe a before and after a diet or before and after some like kind of training to see what the results are. So these are dependent samples, they're quantitative, which makes this a matched pairs t-test. This could also be called a hypothesis test for a mean difference. Now this is different than if we had a two sample t-test. That would be called a two sample hypothesis test for a difference in mean. So the wording here on these last few words is important. If we're talking about the difference in means, that's different than the mean difference, all right? Mean difference is about like taking our samples, subtracting them, finding the mean. Difference in means is having two different means that we're comparing.